This video is on improper integrals. So to start, I've got two integrals worked out on the screen, and one of them is correct and one of them is incorrect. And so I'd like you to actually pause the video and look closely at what I've done and try to figure out which one is right and which one is incorrect. Okay, so when you're looking at it, it's not obvious which one's incorrect. There's not a computation mistake, or at least I hope not. There's the division that we're doing when we do 27 divided by 3 and 2 divided by 10. That's allowed because of the properties of logarithms. The issue is that the integrand, the thing inside the integral on the first problem, that is discontinuous at 2. Oh, I'm sorry, at 1/2. And so this is discontinuous at 1/2. And the one on the bottom is discontinuous at 5. And so if we think about it, we only actually care about one of those. So the one that's wrong is the first problem because 1/2 is between 0 and 5. The second one is okay because even though it is discontinuous at 5, that's not between 0 and 4, so it doesn't affect the problem at all. The fundamental theorem of calculus, which is what allows you to do this first step, so that one is true, this one is not true, so this is not equal. The fundamental theorem of calculus says that what you're integrating needs to be continuous on the interval AB. So the function would need to be continuous from 0 to 5 on the first problem, and it's not. The function needs to be continuous from 0 to 4 on the second problem, and it is. And so the second problem is fine, the first problem is not. Okay, so the first problem that we're looking at there is an example of what we call an improper integral. And so we're going to look at several of those. And so I want to start by looking at an example. And so let's look at the example, the integral 4 to 10 of 1 over, we'll do x minus 4 squared dx. Okay, and so when we're doing this problem, it helps to think of the problem graphically. The reason this is an improper integral is because the function that we're integrating is discontinuous at 4. And so I want to look at a graph. And if we look at a graph, 1 over x minus 4 has an asymptote at x equals 4. And it has two parts of a hyperbola, kind of like this. Or well, what started as a hyperbola, I guess not a hyperbola, but looks like that. And so anyway, it has two parts like that. And so then if we look at the asymptote at x equals 4, what we want here is the area under the graph from 4 to 10. And so we're looking at that. And it's weird to even consider that that could have an answer that's not infinity because it's an open area. So the area is not closed. But the idea is that the graph gets very close to the line x equals 4, and it actually gets infinitely or arbitrarily close to x equals 4. And so when we're looking at this, there are two kind of cases as to what could happen. When we go from 4 to 10, we can't do that integral directly, but if I did the integral from 4.1 to 10 of 1 over x minus 4 squared, that would be a proper integral. Or if I did the integral from 4.0001 to 10, that would also be a normal proper integral. And if I did the integral from 4 point a lot of zeros and a 1 to 10, that would be a normal integral. If we drew it on the graph, those regions would be closed, so it would be a finite area. So these for sure would all have answers. Now, I'm going to make up some potential answers. So potential answers, but not correct answers. There are two possibilities kind of for what could happen here. So one thing that could happen is that maybe this, and again, I'm making this number up, but maybe this answer is 24.87 4.926. And then when we go from 4.1 back to 4.0001, that is a really tall strip that we're adding there. So it's very, very tall, but it's also very, very thin. So it's possible that it doesn't add much area. So it's possible maybe that now it's 24.99925. And again, I'm making this up, and maybe there's one, who knows. Maybe it's that. And now when we add these extra zeros and get even closer to 4, maybe now it's 24 point, a lot of nines, 624 or something along those lines. And so again, those are not the correct numbers, or I'd be surprised if they are. But now if this happens, then what we would say is that the original integral converges we would say this converges to 25. Another possibility is that this could be 24.87926 still. And again, I'm making that up, so it's probably not. But then when we add in this really thin strip, it's also so tall that it adds a lot of area. So maybe by now it's 1,472.916 or something along those lines. And again, I'm making up that number. But now by the time we're down here, maybe it's 24 or 245 million or something along those lines. In that case, we say, okay, well, the integral or that area approaches infinity, and so then the integral diverges if that happens. So that's a loose explanation of what can happen with an improper integral. A textbook will define that very specifically, and so we're going to talk about it in terms of limits in this video, but we're not going to do a formal definition of converge and diverge. We'll do more of that when we get to what's called sequences in series. But this is the idea, the intuitive idea behind it. If we do the integral as we get closer and closer to 4, if the area is approaching 25, we say that that integral converges to 25. If it's approaching infinity, we say that the integral diverges. And so we'll see some more examples of that and exactly what that means as we proceed. But let's do this problem. So what we were doing there it is not necessary for the problem, and it's definitely not the way you work the problem. But when we do this, the idea is we look at that problem and we say, okay, we don't really know how to deal with that. So we don't know how to do the integral from 4 to 10 because it's discontinuous at 4. The function there is discontinuous at 4. So what we're going to do is we're going to say we're going to do the integral from r to 10 instead. And then we're going to think about what values of r we care about. So what we care about, we don't care about like if r is 30. And we don't care about if r is 2. What we do care about is if r is 4.1, or if r is 4.01, or if r is 4.00002, or something along those lines. So we care about numbers that are getting infinitely close to 4 from the right-hand side, from the positive side. And so what we're going to do is we're going to look at the limit as r approaches 4 from the right of that expression. And so we're going to do the antiderivative. So I'm going to go ahead and rewrite this as x minus 4 to the negative 2. Whoops. Let's do the integral of that. That's a quick U substitution problem. And so we do 1 over negative 1, x minus 4 to the negative 1, evaluated from r to 10. Now, we're allowed to do that here because r is not 4. R is something that is close to 4, and it's to the right of 4. So between whatever r is and 10, the function inside the integral is continuous. So we can apply the fundamental theorem of calculus and do this. So now we're going to simplify that. And now we're going to get the limit as r approaches 4 from the right of negative 1 over 6 minus negative 1 over r minus 4. And now we're going to think about what happens as r approaches 4 from the right. So as r does approach 4, 1 over 6 or negative 1 over 6 won't change. But we're in the second fraction thinking about something like 4.001 minus 4 in the bottom of that fraction. If that happened, 4.001 minus 4 is 0.001. And then 1 divided by that is 1,000. It's minus negative, so it ends up being plus. So we'd have negative 1/6 plus 1,000. As we add more zeros and as we get closer and closer to 0, the bottom gets closer and closer to 0. It becomes like 0.000001. And then we have 1 divided by that. So this approaches infinity. That's a limit that we look at in Calc 1. But if you have 1 over a positive number near 0, that's going to approach infinity. That means that in this case, we say the integral diverges, which means that something like the case in red up here is what's happening. Again, those numbers are made up, but as we get closer and closer, even though it's very, very thin, it's tall enough that it adds infinite area there, and so the area is open and it's infinity. Okay, let's look at another example. So let's look at the integral from 4. Let's do actually 6 to 10 of 3 over the square root of x plus, x. We're going to do 10 minus x. Okay, and so if we do the integral from 6 to 10 of 3 over the square root of 10 minus x, again, it's helpful to think about the graph. There's an asymptote here at x equals 10. The negative x reverses the direction of the graph, and it looks something like this. And we're going from 6 to 10. So again, we're looking at an open area, but it's possible that that gets so close to that asymptote so fast that it doesn't approach infinity. And so we have an area that we would consider to be finite, or it converges to a finite number. And so we're going to look at the limit as r approaches 10, but from the left-hand side. And so from the negative direction, we care about numbers like 9.999, not 10.001. And so we're going to do the integral from 6 to r of, and then I'll go ahead and rewrite it as 3 times 10 minus x to the negative 1/2 dx. Now that's a quick u substitution where u is 10 minus x, du is then negative 1 dx, and so we get negative 3 times 1 over 1/2, which will simplify to 2, times 10 minus x to the 1/2, evaluated from 6 to r. We simplify that as much as we can. So we get negative 6, and then I'll go ahead and write it as the square root of 10 minus x from 6 to r. Let's make that 6 just a little bit neater. And now we've got the limit as r approaches 10 from the left of negative 6 square root 10 minus r minus negative 6 square root of 4, because it's 10 minus 6. Now, as r approaches 10 from the left, 10 minus r approaches 0. The square root of 0 is 0, and 0 times negative 6 is 0. So we get 0 plus 6 square root of 4. Square root of 4 is 2, and 6 times 2 is 12. So we say that the integral converges to 12 this time. Okay. Now, there are several ways for integrals to be improper. One way is these first two that we're talking about, where there's a discontinuity at one of the bounds. So here there's a discontinuity. The first problem we did, there's a discontinuity at 4. The second problem we did, there's a discontinuity at 10. There's also possible that there's a discontinuity in the middle of an interval or somewhere in between the two bounds. And so if I looked at a problem like this, if I said, okay, we've got the integral from, say, 10, I'm sorry, we will do 7 to 10 of 3 over the cube root of 2x minus 16 dx. Now that's continuous everywhere except 8, but 8 is in the middle, or in between 7 and 10, not in the middle, but in between 7 and 10. And so if we look at a graph, the cube root, 3 over the cube root of x, looks about like this, except there's an asymptote at 8. So that's at 8. And then we have a graph that looks about like this. And so we're looking at the integral from 7 to 10. So if this is 7, we're looking at that area, and then 10 maybe over here, and we're looking at this area. And again, maybe those are both infinite. If that's the case, we would say that the integral diverges. Maybe they're both finite, and in that case, we would say the integral goes to whatever the total is, where the the area underneath the x-axis would count as negative. And so the way we would do this is we actually split this into two integrals. So we need to do the integral from 7 to 8, and we'll go ahead and rewrite it as 3 times 2x minus 16 to the negative 1/3 dx, plus the integral from 8 to 10 of 3 times 2x minus 16 to the negative 1/3 dx. And now we're going to do two problems like the ones we did above. So we're going to look at the first one, the limit as r approaches 8 from the left of the integral from 7 to r of 3 times 2x minus 16 to the negative 1/3 dx. And now we're going to look on this one at the limit as some other variable, we'll say t, approaches 8 from the right of the integral from t to 10 of 3 times 2x minus 16 to the negative 1/3 dx. Both of these are quick u substitution problems where u is 2x minus 16, so du is 1/2. We can then, du is 2 dx, which means we're going to get a 1/2 outside. And so we're going to do the limit as r approaches 8 from the left of 3 times 1/2 times 1 over 2/3 times 2x minus 16 to the 2/3 evaluated from 7 to r, and we'll simplify that in a minute. And then the same thing here. The limit as t approaches 8 from the right of 3 times 1/2 times 1 over 2/3 times 2x minus 16 to the 2/3 from t to 10. Whoops. 2/3 there. From, man, I am struggling. So, all right, so 2/3 from t to 10. And now we'll simplify and subtract. So we're going to get the limit as r approaches 8 from the left of 9/4 times 2r minus 16 to the 2/3 minus 9/4 times negative 2 to the 2/3 plus the limit as t approaches 8 from the right of 9/4 times 4 to the 2/3 minus 9/4 times 2t minus 16 to the 2/3. Okay, now as r approaches 8, 2r minus 16 from either direction, 2r minus 16 approaches 0. So this first expression becomes 0 minus 9/4 times negative 2 to the 2/3. And then on the second one, we get 9/4 times 4 to the 2/3 minus 0, because as t approaches 8, that second expression or that last expression approaches 0. We can simplify this a little bit, so I might make this 9/4, negative 9/4 cube root of 4 plus 9/4 cube root of 16. Beyond that, there's not much we can do without a calculator. I guess we could make it into prime numbers, but there's no real need for that. And so we would say that we can either say this is kind of the answer, this is the answer, or we could say converges to that answer. Okay, and so this is how we handle improper integrals where there's a discontinuity at either endpoint or where there's a discontinuity in between the two endpoints. In all of the cases, or in this case, it is understood that if either of the two integrals diverge, then the original integral diverges. That's not true when we get to series, where we're going to have some similar thinking to this. But when we talk about improper integrals, if either of those two integrals diverges, then the original integral diverges as well. It would be worth looking at the textbook for the formal definition of these, but we're going to go in the next video into another type of improper integral. They're easier to identify, but it's when you have infinity as one of the bounds. So we can talk about things like this. So we could do like the integral from 4 to infinity of 1 over x to the 5th dx and talk about the area under that. That'll be the first example on the next video. Thanks for watching this one.